Welcome to Libertarian Counterpoint. I'm Lee Welter. Joining me on the panel are David Peters, local IT consultant, and Tom Tamarkin, who is president of USCL Corporation, as well as another company called Energy Site.
Correct.
Is that correct?
Yes.
Libertarians have been focused on dealing with what we libertarians consider humanity's biggest problem. That is dealing with oppressive or tyrannical government. Tom's focus has been humankind's second biggest challenge. That's harnessing energy to put to productive use. Many people don't realize our whole flora and fauna on the Earth are dependent on nuclear fusion as its fundamental energy source. The sun turns hydrogen into helium, releasing energy in the form of radiation. Plants photosynthesize that radiation using carbon dioxide as a fertilizer to create energy-rich foods, which in turn are consumed by animals, and we omnivores take advantage of a little bit of all of them. But Tom, you have a focus on the economics and the realities of energy sources, and I was going to say impending shortage, but I'd say very real shortage at this point.
Oh, absolutely.
And the fuel price is not just a piece of it.
Of course.
So tell us more.
Okay, well, let me expand upon that concept for a minute, if I may. If all peoples of the world were to live a comfortable life and have the ability to prosper, we would have to increase the total world energy production by a factor greater than 10 times. That's not possible, and if it were, of course, we would deplete fossil fuels by the end of this decade.
Not possible yet, you mean?
Correct.
Oh, good. You're getting to the good part.
Okay. Today, the United States has roughly 4% of the worldwide population, yet we use about 28% of the world's annual energy production. Alternative, green, and renewable energy sources, well, frankly, they can supply less than 4% of the projected 2050 total energy requirements.
So is that worldwide?
Worldwide, of course. There's only one way to produce the amount of energy needed to support mankind once fossil fuels are depleted. That is the conversion of mass into energy, as Albert Einstein taught us in his special theory of relativity. We do this through a process called controlled nuclear fusion. As a matter of national security and as a moral imperative to safeguard the future of the world, the United States should immediately take action to achieve this goal and demonstrate this process of controlled fusion by the end of this decade.
When you talk about nuclear energy, people think of fission, which is our current source using uranium and unstable isotopes. Produces some scary situations, but it's also been powering our Navy fleet for decades and very high degree of safety. But fusion is something different. You're going to explain it to us, I think.
Well, a couple of comments are in order. Frankly, the nuclear industry throughout the United States and the world, Europe, is probably the safest industry of any industry on Earth. When we look at the aviation industry, we look at the petrochemical industry, we look even at the transportation industry, there is no more safer industry than the nuclear power industry. So, having said that, what happened in 1979, we had 3 Mile Island and a very, very small release of gaseous radioactive waste, which frankly caused no harm, but it was sensationalized by the media. And from that point on, anything with the term nuclear is, to the average person, highly suspect just because they don't have the ability to gauge the safety factor.
Yes, and it's a topic of the scaremongers. I'm too cynical at times, but I suspect that the folks that are profiting from our current fuel sources are suppressing the use of nuclear energy because it would be serious competition for them. Do you think that's possible?
There is a common school of wisdom, if you will, that would suggest that that's true, and that large companies in the petrochemical business and other businesses, primarily in petroleum, have suppressed this technology. We actually did a investigation and wrote an article which I can make available to anybody that's interested by contacting us at the website. And through an extended process of interviewing literally hundreds of people, we actually found no evidence that that in fact happened.
Oh, that's good. So,
well, one of the technical aspects of fusion are the immense amounts of energy to get the cycle started. It was only a few years ago they were able to do it at the Sandia Labs in Livermore to get enough, they used lasers to start the reaction and actually got it to sustain itself, but they let it stop because they didn't have a way to contain it.
Well, before we get too involved in specific embodiments of fusion, because you mentioned Lawrence National Laboratories, that is one type of fusion, if you will. Yeah. There are other types of fusion involving magnetic containment, which are probably even better understood and have a longer history. So let's take a minute and describe what fusion is. We talked about fission. Everybody, of course, is aware of atomic power and fission. In Europe, 35% of all power comes from fission reactors, and that's been the case here over the last 30 years. In a fission reactor, we take heavy nuclear materials such as uranium, plutonium, thorium, and through a reaction we actually split these elements into a subset of different elements, and in so doing we release an amount of energy, tremendous amount of energy, but we also release a significant amount of radiation and the new elements that are formed. You take uranium-93 and through an actide chain it spins off in 2 or 3 other elements very quickly. These tend to be highly radioactive, and of course these radioactive wastes have half-lives of literally 25,000 years, which means 25,000 years, the amount of mass of a radioactive waste today is only half of what it is 25,000 years later, 25,000 years later. So you go through a...
So we wouldn't want to wait too long for that to lose its
you have to go through 10 cycles. Now, in the process of nuclear fusion, it is the exact opposite. We actually combine elements. So if we take an example, hydrogen, and a specific isotope of hydrogen called deuterium, which is readily available in seawater, and the process of fusion says that we can combine 2 or more atoms, if you will, of deuterium or another isotope such as deuterium and tritium, and in so doing we form an entirely new element, let's say for an example helium, and in that process we release a tremendous amount of energy. In the case of deuterium and tritium, it releases approximately 17.6 million electron volts per reaction, per atom.
And helium is an inert gas, so it's stable. It's not likely to create any further problems.
That's correct.
Unless we breathe it and we talk sort of funny.
It makes you sound kind of squeaky, but short of that. So the process of fusion itself produces no direct radioactive waste. Arguably, the reaction of deuterium and tritium can in fact produce some radioactive material, but it's not a direct consequence. It's a consequence of an indirect action of the neutrons created from that reaction having an effect on materials within the reactor. And that radioactive waste has a half-life of less than 12 years. And frankly, it's alpha particles. It's very low level.
You could stop that with a big sheet of paper or a thin sheet of lead or aluminum or the like.
Yes.
Good. And even fission, as it's currently engineered, I've read, is relatively safe, because one of the concerns is that when that chain reaction starts, if it is not suppressed to some extent, it can rapidly run out of control or overheat or melt or what have you.
Or explode.
But there's some new, what do they call, pebblebed reactors? Are you
well, I
familiar
mean,
with
there's
that,
one
David?
development in Germany where they vitrified nuclear waste, and the theory was that it would go without water as a coolant. It would go up to 1,100 degrees Fahrenheit. And so they, near a big German city, They fill it full of these little vitreous radioactive particles and watch the temperature go up and go past 1100. And at 1102 degrees it stopped because it couldn't get any hotter because they were maintained at a distance from each other by being in the glass particles that held it would melt at 5,000 degrees. So it was the same idea of going in and kicking out a fire by kicking the embers apart.
So there's some intrinsic safety in that,
Yeah,
even
but they won't use
fission,
it because
but fusion is intrinsically safe.
Well, fission
It's just a matter of getting the stuff to work, right?
Actually,
Well, as David said here at the beginning.
The biggest, one last comment, sorry, is the biggest example of fission in the world is West Africa. It's 3 to 5 degrees hotter on the ground than it should be because of the uranium that's still fissioning under the ground in the soil.
You're a fountain of wonderful
Trivia,
pearls of
yes.
knowledge. Oh, no, that's fascinating
But
stuff.
I mean, the thing is, if it's spread out enough, it can't explode. And if it's concentrated enough, it will build up heat, and the heat will turn water into steam, and steam gives you turbines. And so it's possible. The whole Yucca Flat deal was they were going to vitrify it and then leave it for 10,000 years. Why not pour a little water over it and get some steam for... But oh my God, we can't do that. That's using nuclear power.
You can turn that to useful energy, obviously.
Tom has a more ambitious plan.
Yes.
The libertarian view of government is that it should lead, which sometimes happens, follow, maybe happens, or get out of the way.
Which never happens.
You think
never
they need to
happens,
do
but
what
should happen,
that could
especially
happen
in
or should happen. And the Human Genome Project was one of a private enterprise beating the government to the punch in this huge, well-funded project. Is that a possibility with fusion?
Let me touch upon a point that David made here a minute ago, and that is the fact that in a fusion reaction, in order to establish the reaction, and by the way, for those of you that are thinking fusion and cold fusion, let's just set that argument here to rest. There is no such thing as cold fusion, period, end of discussion. In order to actually fuse atoms together, it takes tremendous pressure and tremendous temperature. By tremendous temperature, I'm talking somewhere in the area of 60 million degrees Celsius and up. Fusion is the process by which the sun works. The core of the sun is somewhere in the area of about 80 million degrees Celsius. In order to produce a similar fusion reaction here on Earth, it can take even hotter temperatures in the area of 200 to 280 million degrees Celsius.
It's beyond my comprehension.
In order to create the state from which we can obtain fusion, we take matter and we convert it into something called plasma, which means we strip the electrons away from the atomic structure, from the neutrons and protons, and it becomes highly ionized and highly charged. In order to do that, we have to, as you said, pump energy into it. So every time we actually fuse one atom of deuterium, one atom of tritium together to form one atom of helium, 4 neutrons and the 17.6 MeV of energy that I described, we have to actually put a pulse of energy into that. That pulse of energy could come, as you said, from very powerful lasers, or it could come from the discharge of electronic devices called capacitors, which is the typical approach in the magnetic confinement scenario.
The capacitors, once they discharge.
However, getting back to this concept of a runaway reaction, given the fact that every time you create a pulsed fusion, again, of one atom of hydrogen, deuterium, one atom of tritium, it requires energy. If I stop that energy, then the reaction stops. So it simply cannot go critical. If a fusion reactor were to malfunction, as an example, it literally turns itself off. There's no way that it can go critical or melt down or explode, anything of that nature.
There must be some people who have some objection to it. There always are.
Well, it's the technical aspects of doing it.
Well, let's talk a minute, if we may, about fusion and does it work? Do we know that it works? The answer is absolutely positively. In 1961, our friends, the Russians, detonated a device. It was actually called Tsar Bomba. Tsar Bomba No pun
That's
intended.
fortuitous, isn't it?
Tsar Bomba was the largest nuclear detonation in the world's history, and it released approximately 58 megatons of energy. It vaporized a desert island. It sunburned people 100 miles away. This was a nuclear fusion event which took place literally in less than 1 second. Yet that particular device, as I said, 57 megatons of energy, was enough energy to power the world for a month.
Yeah.
That's impressive.
What was the fuel in those days? Hydrogen and lithium.
Well, that was the difference between a hydrogen bomb, which is a fusion bomb, and a nuclear and a uranium bomb, which was actually encase the hydrogen because
Exactly.
the uranium would go off, causing an implosion to build up the pressures that would simulate the center of the sun, and the pressure generates heat by itself, and then it all of a sudden, but it does it all at once rather than over a period of time. So controlled fusion is period of time, right?
So what are the barriers to getting there from here at this point, other than funding? It's not a cheap process, I presume, at least in development.
Well, the federal government here in our federal government has been working on fusion now literally since the 50s. The work, of course, was pioneered by Dr. Edward Teller, who, after he left the military, initially, the problem was one of containment, in that it's very difficult to contain this plasma, which is 100 million degrees Celsius in temperature, because it literally would melt anything that it comes in contact with.
But you say it's charged, which means it could be subject to electromagnetic forces
fields.
to confine it.
Right. So in the early 60s, Russian physicists developed a technique which became known as the tokamak, which is a toroidal magnetic configuration. We call it a magnetic bottle, which actually confines the plasma to where it doesn't come in contact with anything physical that could, one, drain the energy so it becomes entropic, and secondly, it destroys itself rather quickly. Now, there are two approaches, as I said a few minutes ago, to actually creating a fusion reaction within plasma. They're quite opposite. One of them involves an extremely high density of material, say 1,000 or 10,000 times denser than ordinary matter. And this is the approach that we call inertial confinement fusion. There's a project now at Lawrence Livermore called NEF, National Ignition Facility, which uses about 160 plus lasers to actually focus all of this laser on a very small pellet that's about 1 millimeter in diameter to create this compression in order to get that density. The exact opposite of that, the magnetic tokamak approach, uses very, very low pressures. Roughly 6 orders of magnitude or 6 zeros different from the laser approach. So the government has been funding through the Department of Energy since the 1960s and became very active in the early to mid-1970s, these two approaches. The magnetic tokamak approach was funded by the Department of Energy, obviously, and its predecessor. The laser confinement approach has been funded by an offshoot of the military. And the reason for that is that technology, and specifically the lasers, was developed in the 80s under the Defense Initiative.
As David alluded to earlier, the fission reactors have simply used heat to generate steam to drive turbine generators. Is that right? Or is there a method for producing electrical power more directly from some of these reactions?
Well, in terms of the nuclear reactors to date and fission reactors, that is basically true. There are other techniques, but virtually every fission nuclear reactor now in the world uses this process of heat exchange. We take the heat and we then, as you said, create steam, and the steam in turn drives the turbine. In the case of fusion, there are two approaches. We have this concept of converting the kinetic energy of the heat, again, into a media such as steam, and converting that into the kinetic energy within a generator. Another approach is called, and it's one word, believe it or not, but it's called magneto-hydrofluid dynamics. And magneto-hydrofluid dynamics is a way that we can actually create electricity, if you will, from these highly charged ionized neutrons.
Would that be more efficient, or is it potentially more efficient? Put it that way. We probably haven't done a lot of measurements of these processes.
A combination of both, I believe, will be used early on. One of the interesting things about fusion is an argument involving the concept of aneutronic versus a neutronic reaction. In an aneutronic reaction, using something such as boron in the classic boron-P reaction, we don't create any neutrons. If we don't create any neutrons, then we don't have this confinement problem and the deterioration of materials and the conversion of those materials into something that's radioactive. In that case, however, we're limited to this concept of magnetic hydrofluid dynamics to generate the power.
So that would be the ideal, I presume.
Ultimately, it would be the ideal. It would be
cleaner,
cleaner, and what we basically say is that the ideal embodiment of a fusion reactor produces zero radioactivity. As an interim, because they're very complex things that I'm not going to get involved with talking about here.
This isn't the forum for that.
No. But the easiest reaction for us to actually generate fusion from with today's technology and our level of experience, again, is this concept of the two isotopes of hydrogen, deuterium and tritium. Using the combination of deuterium and tritium, deuterium, of course, can be literally mined from the ocean because approximately 1 in 7,000 molecules of water is heavy water. That is, it's oxygen and deuterium based.
Yes,
so it's very available. I mean, we have enough energy in our ocean to supply the Earth's needs for energy for literally a billion years to come. Then we have to look at this tritium. Where does the tritium come from? Tritium has a half-life of 12 years, so it doesn't exist readily in nature. But we actually can breed tritium in the process of creating this plasma using a little bit of another element which is very readily available called lithium.
Oh, yes, I've heard of lithium before.
Lithium batteries is a common.
Not only that's part of some people's diet just to keep them stable.
Probably a better use for it than anything else. So one of the problems with fusion is, obviously maintaining the reaction and then refueling it without having to stop the reaction. And how does that being resolved, or what?
Well, again, I think we for this audience, I think we don't want to become too terribly.
We don't want to get too detailed.
Most of us are libertarians with Asperger's,
But
so we can deal with the technology of it.
Okay, but if we look at the technology and the science of it, we have to differentiate between an approach that we would call solid state, or not a solid state, but a steady state reaction, as an example in a magnetic tokamak, as opposed to a pulsed reaction as an example in the inertial confined using these lasers. Now, as I said a few minutes ago, you have a tremendous difference between the magnetic confinement and its vaporization, its pressure, which is considerably less than 1 atmosphere. And as an example, the tokamak project that most people refer to today is an ongoing project that has not yet been built in the south of France, which is called ITER. And in the ITER embodiment, the tokamak, the sphere, toroidal sphere, is about 3 stories in size. It's extremely large, and yet the vapor pressure is well under 1/100th of an atmosphere.
Good.
Now, if we look at the difference between that steady state approach and the pulsed approach using lasers, in between we can see that they're possibly now, because we know many things today that we didn't know 20 or 30 years ago when we started this research and development. There are other approaches that we can utilize that do not require a steady state, which means energy constantly being almost in a feedback reaction pumped in, but rather on a pulse basis. And one of the more promising technologies that we're looking at today is a technique called pulsed jet magneto inertial confinement, which uses magnetic targetized fusion capsules, if you will. And in this particular embodiment, it greatly limits the necessity to have that kind of ongoing, almost regenerative feedback that's required for the steady state.
What's your vision for the future, Tom? We only have a couple minutes left here, and you could envision a massive governmental project like the moonshot or something of that nature, but it's hard, and politically, lots of challenges. I would think if you could get investors and fund a private project, you'd get there more quickly and probably more cost effectively, and certainly have a lot of incentives to gather investors. Sounds good to me, but what do you think?
Absolutely. When we look at the tokamak approaches and we look at the internal confinement, or I should say inertial confinement approaches, we have spent over $40 billion over a time frame of close to 50 years, and yet we have not achieved what we call a break-even gain fusion reaction. That is to say, the fusion reactions that we've obtained so far have been relatively short in the area of microseconds or even milliseconds, and the amount of gain, it takes more energy pumped into that system than we actually get from the fusion reaction.
That was my understanding. The Sandia labs had actually minute, but the amount of energy generated was greater than the energy needed to cause the reaction. And then I think they lost their funding because Lawrence Livermore, which is a government institution, couldn't even come close. So there was a little politics involved.
Well, absolutely. There's a tremendous amount of politics in what we call the mainline fusion approaches. Again, tokamak getting the majority of the money, and Princeton Physics Laboratory is there. Princeton Plasma Physics Laboratory getting the majority of it here in the United States. But again, having said that, we talked about the private sector and the fact that this new technology that I mentioned a few minutes ago involving a pulse jet configuration and a spherical confinement lends itself to approaches where it doesn't cost $1 billion to build a test reactor, but maybe 100th or a 250th of that. So all of a sudden, we're talking numbers in the $20 to $25 million range.
So you investors, people with some money to put into it, and certainly you look at, Microsoft is a capitalization of tens of billions of dollars at this point. We can afford our computers. We can certainly afford cheap energy at some point.
Oh, absolutely. There's very fertile ground now for the private sector to come in and actually take this fusion